Hello juniors, today we're going to see electronic assignment 13, which is about trigonometric ratios in the unit circle. We're going to learn how the unit circle works, and you would see that if you remember how to correctly interpret and draw the unit circle in your heads, you would see that finding trigonometric values is actually very easy, and also determining signs of the trigonometric values depending on the quadrant we're in is actually very easy. So it's trigonometric ratios in the unit circle. Objectives for the class are four. Number one, define cosine and sine in terms of the unit circle. Number two, find the exact values of trigonometric ratios. Then apply the Pythagorean identity. We're going to learn about this in this class. And finally, determine the relationship between trigonometric ratios. Okay, so let's start by defining what the unit circle is about. It says, the unit circle is a circle with its center at the origin and a radius of 1 unit. The word unit refers to this, right? We have a radius of 1 unit in length. Okay, so this is a unit circle. It has its center in the origin of the coordinate plane, and the radius is equal to 1. So for example, this point over here has coordinates 1 and 0, this one over here 0 and 1, and so on. -1 and 0, and 0 and -1. So we would see how this unit circle is very important when we relate it to trigonometric values. Okay, then it says, angles in standard position in the unit circle are measured starting on the positive x-axis and turning anti-clockwise for positive angles or clockwise for negative angles. So for example, in this case, we're always starting on the positive x-axis, and we always turn anti-clockwise, or counterclockwise is also the name. That means we go from this to this in opposite direction of the clock, right? So this is what we call a positive angle, so this is positive theta, while this case over here where we start in the positive x-axis but we go clockwise, you see that we're building a negative angle, negative theta. Okay, so that's what we know as standard position. Then we have the four quadrants. This is something basic you should already know. It says the coordinate axes divide the plane into four quadrants labeled first, second, third, and fourth as shown. So this is first quadrant, second quadrant, third, and fourth quadrant. Angles in the second quadrant, for example, lie between 90 and 180 degrees. Okay, so this is something you know. First quadrant is from 0 to 90, second is from 90 to 180, third quadrant is from 180 to 270, and finally the fourth quadrant is from 270 to 0, or also sometimes called 360 degrees, right? A complete revolution. Then it says, this diagram, this one over here, shows a circle, actually this one over here, shows a circle with equation x squared plus y squared equals 1. So, for example, this triangle over here, or actually, it's better if we look at this one. This triangle over here, this point B, has a coordinate x, y, right? So if we build the right triangle here, we would see that the hypotenuse is 1. The x coordinate would be x and the y coordinate would be y, right? So from this triangle, we could say that this is true, that x squared plus y squared is equal to 1. The center of the circle is at the origin and its radius is 1 unit. This is what we know as a unit circle. So here we repeat the definition of a unit circle. In the diagram, the angle theta is positive, right? We're moving from the x-axis and counterclockwise until we get there. Now, take a closer look at acute angles in the first quadrant of the unit circle. OA, which is this segment over here, and OB are radii of the unit circle. So OA equals OB, which is equal to 1. Next, use the acute angle theta to form a right angle triangle BOC. So if you take a look at this triangle BOC right here, it's a right angle triangle, right? Then it says, using the trigonometric ratios in triangle BOC, we would see that, for example, cosine, remember that cosine using SOHCAHTOA? Remember SOHCAHTOA? If we find, for example, cosine of the angle, we would see that cosine is adjacent. The adjacent side is x. So this is x over the hypotenuse, which is 1, right? which is 1. That's what we have here. Cosine of theta is equal to x over 1. So if we solve for x, we're going to have that x is equal to, if we take the 1 to the other side, or if we just leave it there, we're going to have that cosine, x is equal to cosine of theta. While if we do the same thing for sine, sine is opposite over hypotenuse, so it's equal to y over 1, which is equal to y, right? So we can say that y is equal to sine of theta. So this point over here has coordinates cosine of theta for x and sine of theta for y. So this is a very important demonstration because you will now remember how to easily determine the signs of trigonometric values just by remembering that cosine corresponds to x values and sine corresponds to y values. If you remember that correctly, you shouldn't have any troubles remembering the signs. So that's exactly what I show here, right? Cosine of theta corresponds to the x coordinates, sine of theta corresponds to the y coordinate, what you can see here. X for cosine, y for sine. So you see that, for example, in the first quadrant, this quadrant over here, both sine and cosine values will always have positive signs. Why? Because y is positive and x is also positive. Remember that x is positive whenever we're to the right and it's negative whenever we're to the left, and y is positive whenever we're up and it's negative whenever we're down, right? So in the first quadrant, both of them are positive. In the second quadrant, sine should be positive, but cosine should be negative. So you would see that the x coordinates are all negative. These are the cosine values, while the y coordinates are all positive, okay? For the third quadrant, you see that both are negative because we're going left and we're going down, right? So the x values are all negative and the y values are also all negative. And finally, for the fourth quadrant, you would see that the x values are positive because we're going to the right, while the y values are negative because we're going down. So all of these values, which correspond to the x coordinate or cosine values, are positive, while these are negative, okay? So that's something very easy for you to remember if you remember the quadrants, right? Which is something very easy to remember. Okay, so from this demonstration, look at this relationship. It says that sine of theta equals to sine of 180 minus theta. So that means that the sine in the first quadrant is equal to the sine in the second quadrant, or the sine in the third quadrant is equal to the sine in the fourth quadrant. That means that, for example, if we look at this triangle formed here for 60 degrees, you see that its y coordinate is square root of 3 over 2. And if we go to its similar triangle formed in the second quadrant, you would see that here we can form the same triangle. And for this same triangle, we have the same y coordinate, right? Square root of 3 over 2. And that's exactly what we're expressing in this relationship, right? That means that this value we obtain here is the same value we obtain in the second quadrant and you see that this angle is 120 degrees, which is 180 minus 60 degrees, right? So the sine of an angle is equal to the sine of its supplementary angle. Then for cosine, the same thing occurs, but for the first and fourth quadrant. You see that, for example, for this triangle over here, 30 degrees, this x coordinate is the same. If we go to the fourth quadrant, it's the same as this x coordinate over here. You see that they share the same side, which is cosine, right? Which is the x value of the point, the x coordinate of the point, right? So once again, if you remember how to position yourself in the unit circle, you would see that it is very easy to remember. And finally, tangent. Tangent in the first quadrant is the same as tangent in the third quadrant. For example, that's why it's saying tangent of 180 plus theta. If we say sine of 180 minus theta, we're referring to the second quadrant. If we say cosine of negative theta, we're referring to the fourth quadrant. And finally, if we say tangent of 180 plus theta, we're referring to the third quadrant, okay? And whenever you only see sine of theta, sine, cosine, or tangent of theta only, we're generally referring to the first quadrant, okay? So that's just for you to remember. Then it says, looking at your results, the x and y coordinates of any point that lies in each of the 4 quadrants, we can identify the sign of each trigonometric ratio in a given quadrant. This is what I explained, right? If you remember, if that sine is y and that cosine is x, then in the first quadrant, all of them are positive. Remember that tangent, here you have, tangent is sine over cosine. That means if both are positive, then tangent will be positive. Or if both are negative, which is the case for the third quadrant, for example, then tangent will be positive, right? Because negative divided by negative is a positive value. So all of them are positive in the first quadrant. In the second quadrant, only sine is positive, the rest are negative. In the third quadrant, both sine and cosine are negative, and because of that, tangent is positive. And finally, in the fourth quadrant, sine is, all of them are negative except for cosine, which is positive, okay? So remember, first quadrant, second quadrant, third quadrant, and fourth quadrant, okay? Those are the Roman numbers for you to remember. Let me write that here as well. First, second, third, and fourth. Okay. So once again, if you dominate this, the unit circle, you shouldn't struggle with these types of problems. Okay, then it says, the other side of the angle, called the terminal side, will intersect the circle at a point. Angles with terminal sides that intersect the circle at points with the same y value have equal signs. For example, sine of 60 degrees is equal to sine of 120 degrees. That's something I showed you already, but I'm going to show you back again here. If you look at this value of sine, remember sine is a y coordinate, so it's this one over here. You see that for 120 degrees, we have exactly the same y here, right? So we see that sine of 60 degrees must be equal to sine of 120 degrees, okay? So that's true for sine. Then it says sine of 240 equals sine of 300. And you see that that's the same situation, right? For 240, our sine is right here. It's a negative value, this one. And for sine of 300, we have this y value right here, which is again a negative value because we are below the x-axis, okay? Then it says, angles with terminal sides that intersect the circle at points with the same x value have equal cosines. For example, cosine of 60 equals cosine of 300. If you take a look at cosine now, for example, cosine of 60, we're going to look at this value here, which is the x coordinate of that point. And you see that it's the same for cosine of 300. Actually, they share the same side. That's why this value over here is the same as this value over here. So you see how cosine is the same for first and fourth quadrant. Okay? And then it says cosine of 120 equals cosine of 240. Same thing here, right? If you take a look at the x value for 120, you see that this x value is the same as the x value for 240, which they share again, right? That's why cosine of 120 is equal to cosine of 240. If you try doing this in the calculator, if you try this, remember that your calculator must be set up to degrees. You would see that cosine of 60 has the same value as cosine of 300, and that cosine of 120 has the same value of cosine of 240. And this is the graphical interpretation of y. Okay, then it says, angles with terminal sides that are directly opposite each other on a line drawn through the origin have the same tangents. So for tangent, for example, tangent of 60 for this angle over here is the same as tangent of 240, right? Remember that tangent is sine over cosine. And you see that tangent in the first quadrant is the same as tangent in the third quadrant. Why? Because tangent is equal to sine over cosine, okay? So same thing will occur for second and fourth quadrant. The tangent in its second quadrant would be the same as the tangent in the fourth quadrant because of the same reason. Okay, I hope you're understanding this, people. Then it says, in the unit circle, an angle can be used to form a right triangle with a hypotenuse of length 1 and two shorter sides which have coordinates sine of theta in y and cosine of theta in x, right? So from this picture, you can establish the Pythagorean identity, which is the one new formula we're learning today, right? It says the Pythagorean identity gives you sine squared of theta plus cosine squared of theta equals 1, right? this side squared plus this side squared must be equal to the hypotenuse squared. But 1 squared is, again, 1. That's why we have 1 over here. And so that's where the first formula comes from, the Pythagorean identity, which is this one over here. Sine squared of theta plus cosine squared of theta is equal to 1. And then this is one that we have already studied, right? Tangent of theta is opposite over adjacent. So if you take a look at this triangle, the opposite is sine of theta and the adjacent side is cosine of theta, right? So opposite is sine of theta divided by adjacent, which is cosine of theta. That's where we get that tangent of theta is equal to sine over cosine. Okay, this is for you to read. Maybe if you want to reflect on that on your own, you are welcome to do so. Okay, so let's see some examples to see how this works. So these are the two new things we have learned today, besides all of the unit circle and the positioning of the values and knowing that sine and cosine are x and y respectively. It says, example, find an obtuse angle that has the same sine as the given acute angle. So for example, for 1a, I know what happened there. I know. No fail. There you go. So for 1a, we have 70 degrees, and we want to find another angle which gives me the same sine, right? So if you remember from this demonstration over here, we know that if we're given an angle in the first quadrant, the same sine will be repeated for an angle in the second quadrant. And that angle is exactly the supplementary angle of this angle over here. So we would say that sine of 70 degrees must be equal to sine of the angle in the second quadrant. And in the second quadrant, we found it by doing 180 minus this angle, right? We find it's a supplementary angle. So minus 70 degrees. So sine of 70 degrees is equal to sine of, and this is 110 degrees. That means that the other angle that produces the same sine value is equal to 110 degrees. 110 degrees. And if you want, you may try this in your calculator. You can plug in. If you try plugging in, let me do this right here. If we try plugging in sine of 70 degrees, remember your calculator should be set up in degrees for this because we're talking about angles in degrees. If you plug in sine of 70, you get as a result 0.940. And if you do sine of 110, you should be getting the same value. Sine of 110, this is again equal to 0.940. So this is a way to just prove or prove that your result is correct. Okay, so I'm going to leave that in blue. Now let's do part B. Part B says the following: we want to find the same sine angle, but now the angle is given in degrees. So if we work in degrees, it's actually the same thing. Sine of this angle, which is pi over 4, must be equal to sine of its supplementary angle, right? Remember 180, if we talk in radians, 180 is the same as saying pi minus, and this angle over here to find the supplementary angle, so minus pi over 4. So if we solve this, we're going to get that sine of pi over 4 is equal to sine of pi minus pi over 4. That would be 4 over 4 minus 1/4. That's 3 pi over 4. 3/4 pi. That means that the angle 3 pi over 4 is the one that will give me an equivalent sine value. Okay? And as always, we can try that. We can find sine of pi over 4 first. Remember that to do this in your calculator, now you should set your calculator to radians because the angle is in radians. So sine of pi over 4 is equal to square root of 2 over 2. And if you find sine of 3 pi over 4, you should be getting the same value. Let's see. Sine of 3 pi over 4. And I get the same value, square root of 2 over 2. That means that we did this correctly. Now, for part B, let me take this down. For part B, for part 2, this one over here, we're going to be doing the same thing, but now I think it's for cosine. It says, find another angle less than 360 degrees or 2 pi that has the same cosine as the given angle. So now we're working with cosine. So if we have 50 degrees, we need to find, this is part A, we need to find an angle that will give me the same cosine value, right? If you remember from the unit circle, you should remember that cosine is the same for the first and for the fourth quadrant, right? Why? Because here the x is positive, so if I draw an angle in the fourth quadrant, it will share the same positive x coordinate, right? So cosine is the same in first and fourth quadrants. So to find the angle in the fourth quadrant, the rule is that I need to write this as negative 50 degrees, okay? And this is the same as saying, if you want to write it in a different way, this is the same as saying cosine of a complete rotation, which is 360 degrees, minus 50 degrees. So then we're going to be finding cosine, we're going to say a cosine of 50 degrees is equal to cosine of 360 minus 50, that's 310 degrees. You see that the exercise says less than 360 degrees. So 310 is actually less than 360, so that's fine. So cosine of 310 degrees must give me the same value as cosine of 50 degrees. And we can try that again using our calculator. We should set it up to degrees because we're working with degrees in this case. So we're going to write that. We're going to calculate cosine of 50 degrees first of all. That is cosine of 50. I get 0.643. And then if I do cosine of 310, I will get, let me see, cosine of 310. I get exactly the same value, right? So 0.643. That means that we did this exercise correctly. Finally, for part B of this exercise, we want to find a cosine that gives me the same value for 2 pi over 3. So cosine of 2 pi over 3. And again, we're going to do the same thing. Now the only difference is that now the angle is given in radians, right? So we need to find the equivalent angle, which must be in the fourth quadrant because we're working with cosine. So cosine of, we're going to write first of all negative 2 pi over 3. But we can also write this as 2 pi over 3. Let me see, 2 pi over 3. This is cosine of 360 in radians would be 2 pi, right? So 2 pi minus 2 pi over 3. Minus 2 pi over 3. I'll take this down. So if we solve this, we're going to get that cosine of 2 pi over 3 in the first quadrant is the same as cosine of, and here we need to subtract 2 pi minus 2 pi over 3. You can do that in calculator, 2 minus 2/3. That would give us 4/3. So this is 4 pi over 3, which is in the fourth quadrant. So the equivalent angle in radians would be for 4 pi over 3. 4 pi over 3. There you go. So once again, we can check our result by finding both cosine of 2 pi over 3. Remember, calculator should now be set to radians for this. So angle in radians, we're going to write cosine of 2 pi over 3. And I get a value of negative 1/2. And if I calculate cosine of 4 pi over 3, I should be getting the same result. So cosine of 4 pi over 3 is equal to negative 1/2 as well. So with this, we make sure that we did the exercise correctly. Okay? So I hope this is getting clear for you people. Now let's see this last example in which we're going to apply the first trigonometric identity we're learning today. So it says, without finding theta, find cosine of theta when sine of the angle is 3 over 5 and theta is acute. By telling me that theta is acute, we are saying that the angle is in first quadrant. So I'm going to write it as this, first quadrant. So we know that angle theta must be in between 0 degrees, and 90 degrees, right? In order to be in the first quadrant. So that's what the exercise is telling me. So how can I find cosine of theta without finding theta if I only have sine of theta? Well, if you remember from this first trigonometric identity, which is a Pythagorean identity, I'm going to say that sine squared of theta plus cosine squared of theta is equal to 1. This is a typical IB exam style question, okay? This is something you need to know. So if I apply this Pythagorean identity, then I already have sine of theta. So I'm going to write this as 3 over 5 squared, right? Because it's sine squared plus cosine of theta squared equals 1. So you see that my only variable here is cosine of theta, which is what I want to find. So I just need to solve for cosine of theta. 3/5 squared would be 9 over 25. So 9 over 25 plus cosine squared of theta is equal to 1. So then I can leave the cosine alone. So this would be 1 minus 9 over 25. So we're going to get that cosine squared of theta is equal to, this is the same as saying 25 over 25. So 25 minus 9, that's 16, right? So 16 over 25. Finally, to get cosine alone, we would need to, let me write that as a next step, we would need to find the square root, right? So square root on both sides. And we're going to get that cosine of theta is equal to, remember whenever we apply a square root, we need to write this actually as plus or minus. So plus or minus square root of 16, that's 4, and square root of 25, that's 5. So plus or minus 4 over 5. But we're told that theta is acute. And if it's acute, it means that it's in the first quadrant. And in the first quadrant, remember that all values of cosine and sine must be positive according to this part over here, right? Sine is positive, cosine is positive, tangent is positive. So for that reason, let me write that here, because we are in quadrant 1, cosine of theta must be equal to positive 4 over 5. And this would be the result, okay? You see that we never actually found the angle. And with the Pythagorean identity, we found cosine of theta, which is what we were asked, okay? So that's it. I hope this was clear, juniors. If not, please let me know. Thank you for your attention and see you.